Hi, this is Nathan Tintle. In this Learning Goal video, we're going to talk about how to predict the mean and standard deviation of a null distribution, as well as computing the standardized z-statistic using what we're going to call a theory-based approach instead of simulation. We will use the Halloween Treats data to talk about this learning goal. By now, we've looked at a number of different studies together. In some of the studies, and you see a few examples in the top row of this table, we've seen bell-shaped curves when we've done our simulation. Those bell-shaped curves are called normal distributions. They don't always happen, but they often did when we did our simulated null distribution. In the bottom row, we see a few cases where we didn't really get a bell-shaped curve. In a couple of these cases, the distribution wasn't very symmetric. In the Doris and Buzz case, it looks reasonably symmetric, the null distribution that we simulated, but there's some pretty big gaps between the dots. This is important because we're finding that in many cases we do get a similar shaped distribution. And in fact, it's the case that we don't always need to simulate to generate that null distribution. Instead, we can use mathematics in some cases to predict what would happen if you were to simulate. Now this is important because before computers, researchers really could not do many simulations very quickly. It was either impossible or at least impractical. So what researchers did instead was they used mathematical equations to predict what would happen if you were to simulate. These predictions are in large part very accurate, but there are some cases where they are not. And the way you know whether or not they'll be accurate is by checking that certain conditions are met. We'll talk about the way these predictions are made now. For cases we've seen so far, the null distribution will be predicted to be a bell-shaped curve centered at the long-run null probability and with a standard deviation equal to the square root of pi times 1 minus pi over n. This is called the central limit theorem. It's a good prediction of what happens when the sample size is large. That is, when you have at least 10 successes and 10 failures. Let's take a look at the Halloween Treats data. For the Halloween Treats data, there are at least 10 children who chose candy. In fact, there's 148, and 10 children who chose a toy. There's 135. In this case, because both of those counts are greater than 10, this means that the predicted null distribution will look very similar to the simulated null distribution. And in fact, we see that to be the case right here because the simulated null distribution, shown in this graph, is a bell-shaped curve. In fact, it's centered at the null hypothesis probability value of 0.5, and as you'll see in a moment, the standard deviation that we simulated, 0.03, is very close to what the mathematical formula gives us. So to recap, because there are at least 10 children in each of the two groups, the predicted null distribution will be bell-shaped, it will be centered at 0.5, and the standard deviation can be found by plugging into this formula. The predicted standard deviation is 0.0297. The standard deviation as seen in the simulation on the previous page was 0.03, very close. You can then use these predicted values to generate a standardized z-statistic, in this case 0.77. A few words of caution. So why do we need this theory-based approach? Well, before we had computers, this was really a necessity. Conducting many simulations was impossible or impractical. This approach is using mathematics to make predictions about the shape, location, and variability of the null distribution. Those predictions are accurate as long as certain conditions are met. If the conditions aren't met, you should use simulation. What if the conditions are met? Would it be better to just use the theory-based approach? Well, it really doesn't matter when those conditions are met because the two methods, simulation and theory, are essentially equivalent.